I hardly need to motivate why compression is a necessity in modern-day computing. In order to support the constant flow of data across the internet, methods to reduce the time needed to transfer information are paramount. Despite this, most people don't understand the basics of compression. The goal of this video is to demystify one of the more common compression methods in use today. Before we dive into any compression techniques, it's important to understand what compression is. The goal of any compression method is to convert information represented as a list of symbols into another, shorter list of symbols. The process of finding the shorter list of symbols is called compression. Any good compression method also comes with a decompression method, which allows you to reconstruct the compressed data from the shorter symbol list. For example, books are composed of letters, which can be considered symbols. In order to compress a book, you could find a shorter list of letters that can be decompressed back to the original book. Finding a shorter list of symbols, however, is not a trivial task. Consider each word in the book. What if you could assign each word in the book to a code composed of letters so that the book written in code is shorter than the normal book? In order for this to work, the codes assigned to each book word should be shorter on average than the book words. To ensure this is the case, you have an idea. First, you develop a list of all the words appearing in the book you wish to compress. Then you assign each word a rank determined by the number of times the word appears in the book. Finally, you sort the list so that the highest rank words appear on the top of the list and the lowest rank words are on the bottom. We would like to assign the shortest codes to the words at the top of the list and the longest codes to the words at the bottom of the list. So we start by assigning the first 26 words to single letter codes. After all the single letter codes are used up, we can start using double letter codes. In order to compress the book, we simply replace each book word with its assigned code word. However, we must also be able to decompress the book, so we should include a translation table showing the book word associated with each code word. In order to read the book, the reader goes word by word in the coded book and finds its entry in the translation table. Using this method on Shakespeare's Hamlet, the normal book is 133% as long as the compressed book. This number is known as the compression ratio of the book under a compression technique applied. It's a handy measure of how well a compression method performs on a specific input. The higher the compression ratio, the better the performance. A similar compression method achieving higher compression ratios utilizes Huffman coding. Huffman coding works around the same two general ideas that this method utilized. First, that words in an input can all be mapped to their own unique codes. And second, words that appear more often should be assigned to shorter codes. Unlike the previous method, Huffman coding can operate on bits, the fundamental data unit used by computers. As a letter is a symbol with 26 states, a bit is a symbol with 2 states, 0 and 1. A Huffman coder takes in a sequence of bits, called a string, and yields another sequence of bits, which can be decoded to get the original bits back. Like the book compression method, Huffman coders break down the input into words. Not English words, binary words. A binary word is defined to be a fixed length sequence of bits. For instance, 0110 is a 4-bit binary word, as is 1010. The job of a Huffman coder is to assign each binary word to its own unique variable length binary code. Once each word is assigned to a code, the input string is encoded by replacing every word in the input by its code. This puts an important restriction on the codes generated by a Huffman coder. Namely, no code may be prefixed by any other shorter code. For instance, the code 0110 is prefixed by the code 011 and is not prefixed by the code 0011. To see why this condition must hold, consider the following scenario. Let's say that the 4-bit words 0001 and 0111 are assigned to the codes 0101 and 01 respectively, and that the input string to be compressed is 0001 0111. With this input string and the code assignments given, the compressed string will be 010101. Upon decoding the output, we realize that we don't get back the input like we expected. In order to fix this issue, we can change the code assigned to 0111 so that it doesn't prefix the code for 0001. Now we can see that we get the input string back after decoding. The reason this issue wasn't present in the bookcoder is because we use spaces to indicate the end of a code. When we are looking at bit strings, where every value must either be 0 or 1, the only way to tell if we have reached the end of a code is by checking if the current bit sequence is one of the codes assigned to a word. The property of no prefixes presents us with an interesting method to visualize code assignments. This figure is called a Huffman tree. The circles in the Huffman tree are called nodes. There are two types of nodes in a Huffman tree: word nodes and combination nodes. Combination nodes have two children, which are connected by edges. Each edge represents one bit of a code assignment. Finding the code assigned to a word in the Huffman tree is done by finding the path from the top node to the word node. At every node, we are presented with two choices. We can either go to the node's left child or the node's right child. Whenever a left branch is taken, we put a 0 at the end of the code. Whenever a right branch is taken, we put a 1 at the end of the code. Something interesting to notice is that the code assigned to any parent node prefixes the code assigned to its child nodes. In order to fulfill the property of no prefixes, all word nodes must then have no children. Nodes with no children are called leaves because they appear at the end of a branch of the tree. Given that all word nodes have no children, we know that all word nodes are leaves. The only other nodes present in the tree are combination nodes, which always have two children. So not only are all word nodes leaves, all leaves are also word nodes. It's important to know these facts about a Huffman tree, but we still don't know how to construct one. To figure this out, let's take an in-depth look at the inputs and outputs necessary to construct a Huffman tree. The input is a list of words and their ranks, which is the number of times each word appears in the input string. The output is a tree representation of the codes assigned to each word, so that this tree results in the shortest possible encoded bit string. Since the final tree has a word node for each word in the input list, let's first create a node for each of these words. To create a tree from these nodes, we can combine them together to create new combination nodes. Let's consider the effects of combining two word nodes on the compressed output string. Combining two nodes adds an extra step in the path to these nodes in the final tree. Since the length of the code assigned to a word is determined by the length of the path to that node, extending the length of the path to a node increases the number of bits in the code assigned to it. The total number of bits this will add to the final string is equal to the sum of the ranks of the two combined nodes. Since our goal is to have a resulting output string containing the smallest number of bits, it makes sense that we should always choose to combine the two nodes with the smallest rank. Upon combining the two least ranked nodes, we are left with a new combination node. The rank of the combination node should be equal to the number of times it appears in the input. The combination node appears when either of its children appear, so its rank will be the sum of their ranks. This combination node can then be placed into the list with the remainder of word nodes, so that the list is still sorted by rank. Once again, it makes sense to combine the two nodes of least rank. If we continue combining the two least ranked nodes, we will have successfully built a Huffman tree. It may be helpful for you to see some examples of this method in order to fully understand what's going on, so I'll include a link in the description to some more videos of these trees being built, but hopefully this process is now intuitive. To recap, we discovered that the property of no prefixes mandated that the codes must be assigned in a way that allows us to represent the assignments in a tree. This tree is built by always combining the two smallest nodes until there is only one node left, which is the Huffman tree. That's all for this video, and I hope you learned something. Stay tuned for the next video on compression, where we discuss the discrete cosine transform.